Good morning, everyone. I am Vinita, working as an associate professor in the Department of Electrical and Electronics Engineering, RMD Engineering College.
Today, let us see the problem in stability analysis to find critical clearing angle for a system where the fault occurs at the center of the transmission line. And here in this problem, it's a three-phase circuit and the fault is also a three-phase fault. And here the fault has been occurred at this double circuit center of this second line. And here in this system, actually, we have one generator and the output side, one infinite bus is there. For the generator, its voltage is 1.2 per unit and its reactance is 0.25. Similarly, for the infinite bus, its reactance is 0.17 and the voltage is 1 angle 0 degrees. And here it is a double circuit line. For this double circuit line, at two ends of the transmission line, two transformers are connected and both will be connected by means of a transmission line, and the reactances for the transformers and transmission lines are specified in this diagram. And here, as per the diagram, the fault has been occurred at a point P. And here we have to calculate the value of del CC, that is critical clearing angle. So in order to find the value of critical clearing angle, we can analyze the problem in three cases: pre-fault condition, fault condition, as well as post-fault condition. So let us move on to pre-fault condition. So we know the meaning of pre-fault condition. Pre-fault is nothing but before the occurrence of fault. So before the occurrence of fault, it is called as normal condition, that is called as steady state condition. So during this steady state condition, we can calculate its corresponding reactance value, output power, as well as the angle del naught. Okay, so first, to find the value of X equivalent, we can write the expression for this reactance circuit. That is, for this case, we have to assume that there is no reactance in this, there is no fault occurred. So it is pre-fault condition, before the occurrence of fault. So no need to consider the fault point. So if you are not considering this fault point, how will you calculate the equivalent reactance value? This J.25, that will be connected in parallel with these two circuit reactances plus this J.17. Now, this parallel circuit reactances can be calculated as, since all the values are equal, we can write this as 0.15 plus 0.28, 0.15 divided by 2 plus 0.17. That will give the equivalent reactance. Now here, this pre-fault condition, that will be represented by suffix 1. So X equivalent 1 is equal to 0.71 per unit. So if you know the value of X equivalent, from this we can calculate the value of the output power. What is the formula to calculate output power? PE is equal to input voltage into output voltage divided by its corresponding reactance into sin del. So what is the value of input power? It is 0.12. What is V? It is 1. Divided by X equivalent, just now we have calculated, it is 0.71 into sin del. So if we simplify this, we will be getting the answer is 1.69 into sin del. Now, this is a pre-fault condition. As I told you earlier, it is a steady state. That is, pre-fault condition means the system will be in steady state condition. So at steady state condition, we'll be getting the input power, that is equal to output power. What is input power? PM. That is equal to output power PE1. So what is the input power given in the problem? It is given as 1 per unit. The generator is delivering 1 per unit power under pre-fault condition. This is the input power. So instead of PM, we can substitute the value as 1. What is the output power? It is 1.69 into sin del. So from this, if you simplify this equation, from this we can calculate the value of del naught. So del naught is equal to sin inverse of 1 divided by 1.69. That is equal to 0.633 radians. This is the first case. Second, during faulty condition, we have to analyze the circuit. So if you take the fault condition, here the fault has been occurred. That is, the fault is occurred at the center of the second line. So what will happen? This circuit gets splitted. The second circuit gets splitted into two, and this will be connected to this circuit. Now, this circuit can be redrawn. So how can the circuit can be redrawn? Here, this is the common point. Here, all the three reactances are in series. So if you add all the three reactances, it is J0.58. And here, this side, that is in the left-hand side of point P, we have 0.15 plus 0.14. It is 0.29. Similarly, right-hand side of point P is again 0.29. So if you redraw the circuit, here we will be getting the circuit like delta. So here it is 0.58, left hand side 0.29, right hand side 0.29. In this side it is 0.25, here it is 0.17, and then the voltage sources. And now here it is a delta circuit. From this delta circuit, we have to convert it into star connection. So for this, what is the formula we have to apply? So XA, that is equal to these two adjacent reactances, 0.29 into 0.58 divided by total all the reactances, so that we will be getting 0.15. Similarly, XBN, this is B point. So B means we need to take the adjacent reactances 0.58 and 0.29. So again, divided by all the three reactances, and point Pn. So what are all the two adjacent reactances? It is nothing but 0.29 into 0.29 divided by sum of all the reactances. So in this manner, we can calculate all the three reactances by using star delta transformation. After calculating these three reactances, we can redraw the circuit. So now we are converting delta into star. So now we need to draw the equivalent circuit for star. So in the left hand side, we have the generator reactance 0.25. Right hand side, we have the infinite bus bar reactance 0.17. Between, we have the star connected reactances. So 0.15, 0.145, 0.725. Now again, we need to simplify the circuit by adding these reactances 0.25, 0.145, 0.145, 0.17, 0.725. Now this is in star connection. Now you have to convert the star connection into delta connection by applying the formula. So if you apply the formula and convert and if you find the total reactances, it is 2.424 per unit. From this, we can calculate the value for the output power. If you know the reactance value, from that we can calculate the output power PE2. E into V divided by X equivalent into sin del. Substitute all the values, and if you find the value for PE2, it is 0.495 into sin del. And PE2 maximum is equal to 0.495. When will we get this sin del is maximum? When sin of sin del, that is del angle, that is equal to 90 degrees mean we will be getting the maximum condition. So P2 maximum is equal to 0.495. And the third condition is post-fault condition. What is mean by post-fault condition? After the occurrence of fault. So once the fault has been occurred means we have to open the circuit breaker to clear the fault. Now this faulted line is open circuit condition. So no need to represent the second line, that is the faulted line during the post-fault condition. Now you will be having the reactances like this. All the reactances are connected in series. Now, if you add all the reactances, you can find the equivalent reactance. So, therefore, PE3 that is equal to E into V divided by X equivalent into sin del. So, if you calculate the value, it is 1.2 into sin del. Now, again, if you want to obtain the condition for maximum power, you have to apply del is equal to 90 degrees. So sin 90, that is equal to 1. So P3 max is equal to 1.2. From this, we can calculate the value for del max. So until what we can change the angle till the value of pi. So here we can calculate the value of maximum permissible angle del max, that is equal to pi minus sine of Pm divided by P3 max. So pi minus sine inverse of Pm is 1 divided by P3 max. It is nothing but 1.2. So therefore, from this we can calculate the value for del max is equal to 2.155 radians. So now for the equal area criterion, the condition is area A1 should be equal to A2. Therefore, then for PA into D del, that is equal to PA into D del. That is for two areas, we have to apply the limits. For the acceleration area, the limit is nothing but del naught to del Cc. For the deceleration area, the limit is del Cc to del max. Okay, so now for the acceleration area, that is you can already we have calculated the formula for cos del Cc. That is, we need to apply the formula, that is PA is equal to for acceleration, it is PA is equal to PM minus PE, and PA is equal to for deceleration, PE minus PM. So if you apply all the conditions and if you calculate the value for del Cc, we will be getting this formula, that is cos del Cc is equal to this formula, and from that we can calculate the value of del Cc. Therefore, the critical clearing angle del Cc, that is equal to 49.16. So this is the procedure to calculate the value of critical clearing angle for the double circuit when the fault occurs at the middle of the transmission line. Thank you.